Good afternoon, gentle readers, fellow earthlings. Today is July 29, 2024. From a desk with Ross Finlayson here in Seattle, Washington, this breezy, humid afternoon. Welcome to another installment of Moment and Motion. Geometry is motion. So today I am still kind of trying to figure out a little bit about the hypercube distance. What is the hypercube distance? Well, it's the distance across the hypercube. Well, what is it? It's 1. The hypercube distance equals 1. Well, that seems pretty simple, declarative, and non-informative. Well, what dimension is it in? What are the dimensions? What are the units in the dimensions? And in the time-like and the space-like? And what is the order of things? What is the scale of things? Vis-a-vis what is the shape of things? It's a straight line with length 1, hypercube distance. So that's what I was trying to figure out last time. There's quite a fuller development of the context and the ideas about it in the previous talk, hypercube distance. So I suppose then this is hypercube distance squared, which also equals 1, if that's the way these things are going to be. That the idea is that the infinitely many higher orders of acceleration are modeled as an infinitely many dimensional unit hypercube, that the tesseract is a 4-dimensional hypercube, and then past that it's just called 5 cubes, 6 cubes, 7 cubes, vis-a-vis that the square is 2-dimensional hypercube, hypocube, and that the line segment, the unit line segment here is also that. And then the idea is that there's an assignment in these higher order dimensions, that it's length and distance, then velocity, then acceleration, then higher order acceleration, and so on, all the infinitely many higher orders of acceleration as from 0 to 1. Because it leaves at distance 0 and arrives at distance 1, this object, or its wavefront. And then it has to proceed from velocity to 0 to 1, or as with regards to that, there's the idea that it's uniformly all the way accelerating in a sense. And so that when it's considered all the infinitely many higher orders of acceleration, most of them are nominally 0. All the infinitely many higher orders of them. But according to this, at some point in time, this hypercube scale, it'll just equal 1. So that ends up being this infinite product. Here is related in terms of a sort of mathematical derivation called the stop derivative, which is for kind of the opposite of starting, it's stopping. And it reflects taking the infinitely many derivatives on down, getting past 0, and then is reflecting about the infinitely negative many orders of powers there, integrals coming back up, how that gets over the impulse, which is otherwise the floor. So it's about the infinitely many higher orders in double power series, the positive and the negative powers from negative infinity to infinity. Then this hypercube distance is a box upon which to figure that it collapses on down from all these infinitely many higher orders into a unit hypercube or unit cube, with respect to one of the dimensions being time, one of the dimensions being space, and one of the dimensions being length, say. Or as with regards to the distance and length, or as with regards to any particular order of motions, change or gradient or integral, as accelerations is to velocity, as velocities is to displacement, helping to define what that means, because it's actually undefined in classical mechanics. It doesn't have one. There's infinitely many higher orders of acceleration. It's just considered constant acceleration, and then how it got there is not defined. It is built or approximated, it is modeled as of particular solutions that follow it, the tauchronous and isochronous, that in the same amount of time or in an identical amount of time, things happen in this way. And so it is built, it is modeled, it is defined as the sum of history is sum of potentials. But the actually infinitely many orders of acceleration is not defined, usually. So here it's giving that this is a definition then of what would be infinitely many higher orders of acceleration to have one at all. They don't already have one, you see. And so why I'm interested in it is, well, it's because I want to understand the mechanics. And here in these talks about moment and motion, there's quite an interest in mechanics and classical mechanics, and the paleo-classical, superclassical. Where paleo-classical means we're going to all the original canon and finding out what trails were kind of left off. Like the great argument for the vis-motrix, the Galilean plainly, and the vis-viva, which is anything that is dynamics in it along the way. Whereas with regards to the old idea about a javelin, and with regards to Galileo, and it's like it goes up parabolic, it comes back down parabolic. And it's like, well, a spiral doesn't necessarily travel this way. Or the javelin that goes up in a line, and then as it loses energy, falls off in the parabolic. So at least that can be demonstrated as carrying an effect what is attributed to the gyroscopic, or sometimes even to just the aerodynamics. Well, at the same time is quite in effect. Is definitely empirically so. So the example of the vis-viva and the vis-motrix is one of these examples of this paleo-classical, superclassical. And then that gets into the rotational and space contraction and how that shows up even in the classical scales of things. It doesn't necessarily take $1 billion super collider or a $10 billion telescope out at the Lagrange point of the moon, which is a great thing to have, to set these things up and show them and demonstrate them. All you need is a football, for example, or a golf ball. Strike a golf ball, watch it deform. It disappears into a space briefly, and then it flies off, as if via this perfect inelastic collision that occurred between the driver head and the ball. So these are at least things that are available to somebody to kind of have to help explain that. Then when the mechanics that we have, the classical mechanics and just the plain linear things that go into it, are just joules and the energy and such, make newtons and newton meters and what, that at the same time, it had to get there somehow. So this is called Zeno's swath, and the fact that Zeno's arguments are great. And they don't make arguments why motion doesn't happen. They make arguments why it must, and the infinitely divisible, and for the geometric series to have a sum. They do, else nothing would ever happen. So then this is carrying Zeno's further arguments from the tortoise and the various ideas of the archer and the runner, and then the field, the runner, where a bunch of people start running back and forth, and whether they get anywhere. Here's with regards to what happens when Apollo drives his chariot around the Earth. That's the usual idea in the geocentric universe, that the sun rose and fell every day as someone just carting it around. And up it went, and around it went, and up it went, and around it went. So when it reaches an overhead position, it's like at that moment, it's like so. Whereas at the same time, it's gotta have all the way from negative infinity to back around, and all the way from infinity to back around. So it's Zeno's swath here is how it cuts the edge of the field, that a swath is like a strip at the edge of a field. And then the idea is that this Zeno swath is basically what makes the corner of this kind of thing. So that the hypercube, as you might imagine, is pretty closely associated with the hyperbolic. And not just the usual notion of the conic sections and the shape, because it's always got a kind of a focus or with regards to the parameters that define it for the parametric forms of a hyperbola. It's as with regard to an input and any two dimensions relating to each other, that they are being inverse. And then when all the dimensions, for example, have their identity together, and call that the identity dimension, then they have this infinite dimensional hyperboloid, which is the product of all of its points at any one time equals 1, sort of a thing. Yet a little bit so where that it also reflects geometrically that it's just like the corner of a hypercube, but it's not pointy, it's rounded. That then this was turned also into this hat style analysis to take the hyperboloid, flip it over so that its legs are downward, and the inflection point to say that there is one, because the inflection point is usually where a curve changes at all. And so it's like the hyperboloid is sort of always, it never changes so much from one way or the other, that it has one. And that's a little bit loose in attachment, the inflection point. Yet for the hyperboloid, it's to effectively reflect that either arm then is symmetrical off to infinity. And then as according perspective, from either side, there's no way to distinguish that from the origin, this offset. And then the hat analysis is to bring that down as if carrying it out the origin, so it flattens out as if filling the entire quadrant of the positive numbers of the xy plane, or xyz, or E1, E2, E3, E4, E5, E6, E7, E8, E9, ... any finite or infinite dimensional vector basis according only to the positive numbers, this identity dimension, that the even and odd and the various of the multiplication of these formulas are simplified by just dealing with magnitudes. That this hypercube and the hyperbolic effect, that the Zeno swath is closely related both in the stop derivative and then for this hypercube distance. So I made this up myself. And even just talking about through this last time, after 30 or 40 years of studying mathematics kind of thoroughly, and with the goal to understand the least amount of mathematics necessary, the foundations, just the numbers, please. Vis-a-vis having a mathematics degree and getting into higher order applications and into numerical methods, or exploring and exploiting the power of a computer to fill out about 50,000 pages of a numerical method to arrive at usual sorts of estimators and such, or approximations, as with regards to the proper modeling of error terms when computing the numerical methods and their approximations, and as with regards to the design and configuration of experiment and this kind of thing about numbers. Getting back down from that, the applied, the great and tremendously useful world of the applied, back then down to the simplest pieces, the origin, the singularity. Then it's like, well, is it 0, 1, 2 to keep it simple? It's like, no, the way to keep it simple is 0, 1, infinity. They form a relation. That's kind of the easiest way to start counting from the beginning, as the same as from the end. So then what this has gotten into is with regards to moment and motion, or a moment being is about something that changes and changes how it changes, and that motion is just the state of something in its flight, in its state as well, that they both reflect complementary concepts with regards to each other about the same thing variously, moment and motion. So the moment is like a pause, or it's when something has an inflection, or it's when something turns. Whereas a motion is when something is like, it was already in motion and it moves. And something that is a moment is like, it was or wasn't in motion and it moves. Galileo put it, and so it moves. He was talking about the Earth and the Sun, and the Earth not being the geocentric stationary center of the universe. But the world does revolve around you still. That's a different story. That's about the development of the maturation of philosophy, and that as you mature in philosophy, or as many do, they learn and theorize as the development of their object sense, word sense, number sense, time sense, sense of a continuum, sense of self, and a theory of mind, that they get into why they exist, why other things exist, whether they are material, whether other things are material, whether they are objective, whether other things are objective, whether they are subjective, whether other things are subjective, and the object-subject distinction, to arrive at this kind of like, it's so either way, it's unfalsifiable if there's free will, but you might as well act on it because that's what it is. Or it's that reality is not just a good idea. In at least one theory, and one of which is reality, it's the law. And then for Platonism, and it's like, yeah, well, of course, there's the whole canon that you can't really get there. There's not really a map to a theory, because you have to have the deductive apparatus to kind of arrive at why nothing and something are flip sides of the same coin. They are the same exchange. They're the same medium of these things. So that said, it does help a lot to have not just the didactic approach to the inductive inference, but very clearly and carefully helping the establishment of like, well, when two things are contradictory, they either can't both be so, or there's something else going on. That those are two different things that also don't contradict each other. And vis-a-vis the usual linear curriculum, which really speaks to the importance of having a linear inductive curriculum for all such matters of what's expected to be known by everybody, which is stated only in terms of what we call axiomatics and forward inference. There are limits to that then. Then is when we get to basically the idea of the limit, or the inductive limit, and the limit of sequences in diminishing differences to reach a constant value, Zeno's arguments, then these are usually introduced in primary school and passingly. I mean, it's about the same time that infinity enters the lexicon and is well defined as when other things are not. It yet remains. That's the way it is. So then with regards to then the very particular notions of mathematical rigor and formalism, then it has to be kept so that the theory is constant, consistent, complete, and then concrete. Constant in terms of that it's got a constancy of terms, that definition is definition, as it makes something finite, as it arrives at terms, predicates, and relations for theory, whether it's terms in relation or relations in terms, according to predicates, theory, logic, that being logic's terms, predicates, and relations, And then for mathematics, a theory of relation, whether it's set theory, a theory with one relation, an ordinary theory, a theory with one relation, two different kinds of objects, arithmetic and algebra and geometry, at least three, all one theory in just a language of words, some comenius language of all truths. That then this arrives at, usually enough, what's called Platonism, and these days sort of a modern paleo-classical, super-classical, strong mathematical Platonism for Plato, one of the traditional canon's great philosophers, that it arrives then in the universals and particulars of these things, that it's constant, consistent, complete, and concrete, at least one theory. Then anything else can be put up against that as a test to say, well, I might not have all of this theory, but I got logic, and I got mathematics, and I got all these objects. So insofar as they stand up, then anything else can be put to them to examine or to test these things, to see that they show or see that they don't. And then as with regards also to how then that gets into the fuller idea of the continuum's foundation, and it kind of starts, from first principles, none, and its final cause, what? It's like, yeah, es muss sein. This is a phrase, it's kind of from the unbearable lightness of being. So it was a novel, but what it reflected is es muss sein, is it must be. That there is one at all, it is. This is kind of the idea that logically you can arrive at, if there's a consistent or constant, consistent, complete, concrete theory, that if there isn't, then forget about it. But that's not very satisfying or even palliative to people with a strong mathematical conscience, that there is es muss sein, it must be. It must be. So when Kant and Hegel have that, like after Leibniz in the monology, and Descartes as giving a thinking realism, and then Kant with the sublime, he's like, well, it's still got to be infinite. It's still got to be sublime, greater than itself, what we would otherwise make of it. And then Hegel said, hey, I'm a perfectly rational modern scientist and a logical positivist, and I've established that it still must have this fuller teleology, because otherwise that's just empirical falsificationism, and it's not just a theory of science, it's a theory of not thinking. It's just a state of sensual subjectivity. So we got stronger mathematical Platonism, stronger logical positivism for a constant, consistent, complete, and concrete theory. And that would be that, and as if that's enough. And it's like, yeah, that's the idea. It's like any putative theory of everything also has to be that. Not that we know what it is, not that we're without our limits, but it is. And so anything else that shows up is not without its limits, can be put to the test of that. And what people have that is logic and mathematics, first cause and final principle, empirical and science, and the entire philosophy is science, the statistical method, and all such matters of science. So it's a strong theory somehow, and then as we get into then having to deconstruct its components, it's like, well, we got the space-like, the time-like, and the light-like, and what that means is the time-like is pretty much definitely infinitely divisible, and the space-like is pretty much definitely infinitely divisible. As far as we can tell, there's only one ray of time, but there's, at least 3 dimensions of space. And they're all one continuum somehow. And then the light-like is just like, well, it's just kind of like the receding of things. It's just that natural limit of the flow and flux of some kind of these 4 quantities, this one dimension in this 3 + 1/2 dimensions or whatever it is. The theory, that all the theories like physics add up to. And everything above that, then the idea being this, like, without other input, the sum of histories, sum of potentials has that physics so follows. Natural philosophy of least action, and just the constant progression and change of things since the beginning of time, or the universe, or inception, or for any thinking, reasoning being, from like the beginning to the end of their consideration. And it varies for people whether that's a continuum, or whether time is experienced, or how cognition works and reasoning apparatus, the experience of events currently and futurely, vis-a-vis people who just kind of have a clock hypothesis, and it's always in the river, in the flow of time, on the river, in the flow. So then that gets into, for these didactics then, and the formalism, it's like, well, when we don't have anything well-defined enough, like for a computer definition, we say, well, if we're going to write a program, it has to be well-defined, or it's not deterministic, it's indeterministic. Some things are, and that's just the way it is, but the definition is key to things, to have a constancy in definition. So that formally, you can't refer to quantity A and quantity B unless they have this derivation that establishes for their definition that their definition and derivation match, and that if another object C and D matches A and B via extensionality, there's a way to apply them as same. Entire notion of formalism and definition and reduction to constants and terms is abstraction and the lifting of that. That's mathematics in its abstraction, and the application of mathematics as it's pure mathematics is a minimal model of model theory that results something is what it does, and it does what it is. Its name is what it is, and it is what its name is. And then for mathematical objects, that they have this abstraction as being merely representatives from the universe of terms, predicates, and relations of theories of a theory. This is the ideas of the template theory. The elements, the primeval, the very fundamental, that which exists before it exists, which does, and here also as the quasi, the pseudo, the degenerate, these all being these primeval sorts of forms of the elements, because then fundamentally, once it's like we have a theory and there's one thing in it, everything is as of a type of this element. So axiomatics and its elements, like the elements of Euclid, the elements of chemistry, and these kinds of things are in the elements of type theory. These things are very elementary, fruitful, and useful to getting this sensibility, fungibility, and tractability for all the desiderata and requirements of a putative theory for foundations or anything. A good theory, a working theory, and that's the way it is. So that's a bit of a digression, and I kind of employed a bunch of different terms that I've collected over a long time, to express the qualia of these desiderata, what's desired, and the requirements, what's necessary of the theory, to arrive at then, thusly, one that is a pretty good theory. That there is one at all, it's the best, very best of the theory. It's all the possible true theories there could be. One of them, which we don't necessarily obtain, but we attain to. Thus from it we may attain and obtain all of the results of the theory. Here's this Graustein, and it's a book of higher geometry. So I figure if hypercubes and this hypercube distance is a thing, then he might have something to say with regards to geometry. So he describes groups of geometrical transformations. So it's from 1930. So it'd be a time when the development of the language of the objects of geometry was at once coming from a very refined place from just the geometers, and at the same time this algebraic geometry and algebraic geometry, those being kind of two schools putting together algebra on the one side and geometry on the other, which are kind of at odds and shoehorn into each other, or break at the edges, or largely in the field they match algebraic geometry and algebraic geometry. This higher geometry then will have a slightly different language. So it belonged to a Moncrief Smith. So it's a series of mathematical texts. It's from Macmillan. It's an introduction to the subject. We looked at this a little bit before. Synthetic and analytic methods. Of the two, the analytic methods are the more indispensable. Without them, in particular, without the simple introduction of imaginary elements which they afford, the handicap is severe. See, that makes for function theory in the entire world of the analytic as of the complex analysis and the Eulerian Gaussian, and it makes for that's useful for a lot of things. But this hypercube distance we're talking about is not imaginary at all. It's real in infinitely many dimensions. It's positive too. But so the analytical just reflects the formulaic and the parametric, the ability to establish analytical character and analysis. And there's a great facility and utility in the Argand and Wessel, and to model fine transformations and then rotations, and also to establish in many manners of relation that the Cartanian, as was discussed here, the Cartanian, which has complex numbers and hypercomplex numbers, greater, richer structures up above the usual notion of an attachment about Euler's formula, e to the I pi equals -1, and various analytical results in the Gaussian after that. That the Eulerian Gaussian analysis is a branch. And that means both senses of the word. It's a principal branch that equals Euler's formula, and then it's a principal branch that Gauss picks his branches, and it's just a branch of analysis. It's not like always there. It's as we were discussing in terms of abstraction and model theory at all, anything that can fulfill the same requirements does the job. And whereas the desiderata is, then it works with all these other kinds of things nimbly, sensibly, fungibly, to be tractably. With regards to that, usually tractably in the complex analysis means we can throw it at our superscalar with our Fortran, and we have a complex number type, and our numerical method library is provided. And it's like, that's great, I guess you won't be needing that entire sheet of trigonometric identities then. Now I'm just kind of picking on the Eulerian and Gaussian, which is great, but it's not always necessary, and in some cases it gets in the way with regards to the analytic and synthetic methods. Then other times, sometimes people will say the analytic, and they mean not making the analysis into the analysis of the maturation and like the entire coordinate space. We can definitely put it on the Cartesian map somehow. But to result is like, well, I just have a small derivation here. It's just a spinning top. It goes around in a circle. Locally, the local analysis situs. And this is more of the analysis situs. So we have to be careful in inspecting the language and interpreting then what they introduce and demand as definition, that analysis doesn't always mean analysis. And analytical doesn't necessarily always mean not neglecting other analytical character of great and profound and necessary interest. And then the synthetic is, as with regards to then a little bit more of like the ad hoc methods usually. Means, well, I found these 2 points there and I need to interpolate them, so I connected them with a line, and the middle of that line is their center. Perfectly suitable sometimes. How and why it is requires its justification. So the analytic and synthetic for the anaphora and cataphora have that the anaphora and cataphora reflect kind of like these universals and particulars. And so just kind of like cathodes and anodes, which reflect in models of capacitance devices, like the vacuum tube of electrical devices, with regards to triodes, pentodes, and such diodes, that the anode and cathode represent kind of the opposite poles of then this continuous process between them. Then the anaphora and cataphora reflect that in language. And so when talking about things like the inductive impasse or induction and deduction, then the anaphora and cataphora should be introduced as they're the things, and help explain that in matters of abstraction and the analytic and the synthetic, that the anaphora and cataphora are kind of omnipresent or always present there in terms of what they represent. These distinctions, whether it's a class set distinction or subjectivity objectivity distinction, anaphora cataphora distinction, or the analytic synthetic distinction, to help reflect in that as we build to a matter of definition and thus reach form, that from a different perspective, that's not form, it's just a mass. The analytical basis and these analytical bridges are two different things. That the analytical basis is kind of like, okay, from here I can see that everything's got a metric and norm, and so it's going to be a fine everywhere. Whereas for an analytical bridge, it's like, I don't know how to get from lines to points or points to lines, but thanks to Zeno and the study of the deductive results out of the way, I know that there's an analytical bridge that meets in the middle of nowhere between them. So that's analysis again too. Vis-viva analytical character, because then we just get into tractable to that there are means. So when this author is describing that the higher geometry demands, he's basically saying, it's like you can put down your compass and edge geometers, though they're perfectly suitable for what they are. And he's just saying that there's not this is just a description in 1930 that it's like now we're going to talk about things in terms of some more modern methods without necessarily going whole hog, as it were, into algebraic geometry. While at the same time, there's much to be gained from the analysis, and then the analysis situs, like from Poincaré and Lefschetz, as we discussed here, so that we have this kind of holistic view that definition is as of the entire world of the terms, and so that we have these descriptive definitional dynamics, thus that over time a great advance in a particular subfield and taking its assumptions and demands of axioms on a particular matter or definition don't block out the view of other perfectly sound definition. Nope, I'm not very much talking about hypercube distance. Yet it is something that now I'll try to figure out something more about it, because it basically just collapses. It just says, well, there's infinite dimensional hypercube. what happens? Well, as soon as you press it, it's like the pressure starts, must be infinitely strong on the outside to where it's 0 and 1, and it's incompressible in the middle. It's like a diamond in the middle. It's like a gas on the outside and a diamond in the middle. And there's an event. There's a contraction. So then the result is then it just results in this box. And its distance, its diagonal is 1. And so then whatever were the terms, the size of the squares, each of the sides is a square. Those become a line because, a hypocube is a square. And a hypocube is just a line, and 0-dimensionally, its length is 1. So he's got many chapters of this book. The very aims of the book dictated the systematic method of exposition rather than the problem method. So the problem method, this helps describe that it's like when you want to show somebody something in mathematics, you give them a derivation and how and why it arrives at it is so. And then the problem method, I think, I'm not too sure what this means educationally or for the curriculum, it's kind of like, here's a problem, here's a story problem. What you gonna do? It's more along the lines of like, these mathematical objects have these properties. You can always so establish the linear development of this derivation that everyone in the class has the same one, and then you can solve it. And then you can solve it how you want. And if you need to show your work, and according to this instruction, it has to use this, and that's how it's done. Our school was pretty easy. To graduate 6th grade, everybody had to know the times tables, and there wasn't really too much to say after that. I mean, to get college credit, you had to graduate calculus. But higher mathematics wasn't really required. It's generally considered, though, that after primary school, that then enters proofs of and derivations of proofs, and axiomatics, and this expository method. The problem method, there's the danger in using it of leaving the student the impression of many striking pictures entirely uncoordinated and apparently without design. On the other hand, experience has shown that a single purposeful picture, which is an organic unit, is more satisfying and will, if it contains enough color, be sufficiently inspiring to stimulate interest. The very notion of abstraction sort of has to be learned. And when there's overload of sensory input, then it's kind of lost, because the abstract world is black and white, meaning it's absent sense. There's kind of no pictures in it. There's only words. There's all the words. Yet. This object sense, number sense, word sense, time sense, and a sense of the continuum have to be developed as phenomenological sensory inputs of otherwise sensual creatures. This sensory, in regards to that's acquired, and it really requires learning at particularly plastic times of the development of the reasoning apparatus, so that fantasy, the imaginary, the abstract, the absurd, and all these things play a full role in separating that then from one's sense of reality. What I'm saying is that I felt that it was really important for my personal development that there was no television or movies. There was only books. And I read everything from cereal. I pride myself on reading. It's like if it's on the cereal box, I'm reading it. If it's in the newspaper, I'm reading it. There's nothing within this entire realm that is not being read. It took a while to get to where I could do that, but at some point in time, I did leaf through the entire Encyclopedia Britannica, because it was there, and so it's. The author talks about something like keep an interest, but it's like if there's that's this isn't meant for that. It's meant to, it's just meant to be. It's just something that is of interest for itself, and it's not accessible to any sensory input. Though this isn't a sincere effort to relay such features of it. Theory. Well, all right then, let's read some more Grashtine's build-up. This book is built around the Erlanger program, which is introduced in geometric form in the very beginning and gradually developed. Klein's fundamental ideas, easier for the student to grasp, was greatly keeping him oriented during the early stages of the geometric development. Another concept that has been brought in at the beginning is that of the rank of a matrix. So what he talks about, doesn't mention elements at infinity. That's one thing that I did like about this book. Homogeneous coordinates, line coordinates, cross-ratio transformations, and complex elements form a formidable set of new ideas. In fact, these new ideas and the order in which they should be introduced constitute the most difficult problem. Their linear curriculum is one thing, with the idea is like it's got to work for everybody, or at least be something that is like you will have had a chance to absorb and internalize this as being a linear development, that it will always kind of be a thing, vis-a-vis all these different kinds of things that then make the concerns and the wider concern has that the richest aspects and the elements of the paradoxical and non-paradoxical, and that which makes order of things, and like and different, and these kinds of things, and universals and particulars. Everybody knows since they learned the word infinity. There's no question that the student finds more difficulty in making his peace with a complex domain than with any of the other new concepts. The complex domain, when it was introduced, was after trigonometry and after algebra, and after most of analysis was already quite well set in. And so you already had at least the parametric real number plane, r squared, the Euclidean plane is attached to a Cartesian orthonormal vector basis, which was always implicit, just courtesy the properties of tuples of numbers, of pairs of numbers. And then with regards to the root of -1, the square root of -1, and that would at least definitely follow there being, positive and negative roots of positive numbers, and the notions of things like the exponent to 0, and that 0 to 0 and 0 to the 0 are not necessarily the same thing. That these are definitely all these sorts of usual concepts about singularity theory being a multiplicity theory before a complex analysis is introduced as like, these numbers are now complex, and so they come in and out of these formulas as making this Eulerian Gaussian analysis, talking about complex analysis and the roots of unity and stuff. Because at that point, before all that other stuff is there, then it's more like, you mean going around in a circle? And be better just to, at least have polar coordinates and all that kind of stuff first. Which is totally like, what do you mean polar coordinates? We just started learning these Cartesian coordinates, and now you're saying you're just going to have everything go around in a circle? But at least they're one-to-one, a distance from the origin and a direction. again, I appear to just be kind of waffling and not really talking about hypercube distance. Yeah, it did have a couple of different things that come into it. I'm reminded the other day I was watching one of these videos, and it was a description of the differential analysis, and then just in passing, I came up in a formula. I was reading it off from some of the derivations in Gonzalez Velasco on the Fourier style analysis, and then I was reading some of the books from the university series of Colson and NC and these other instructors as after in Rutherford and out of the UK and stuff. And so then I was reading one of these derivations and I said, oh, well, in the identity dimension, then works out this formula is like that. And I was like, I think that if I wrote that up, it would be of analytical interest. And so now I'm just waffling some more and saying that when I talked about the hypercube distance and giving it a model of saying that the hypercube distance is like an infinite dimensional box and it contracts. And so it initially contracts and its resistance is 0. And then when it finally stops contracting, its resistance is infinity to go from the infinitely many dimensional to cube. And then in that cube is like a line segment. And then that line is like a translation of like the curve or the turn as it goes from 1 to 0. And it's according to how it goes from 1 to 0. Because in the infinite many dimensional hypercube, it is a straight line between 0 and 1, from corner to corner, and its length is 1. When it shrinks down to it, then it's the curve. So with length 1 of the transformation of the coordinates, which results as the same thing. So it's a modeling of the change as a unit change. But it's a dimensional basis outside of it. Instead of usually the dimensions are like, the dimensions are perspective, and perspective, they do not change. Everything else is parametric in them. This is just that inside out. It's that simple. Because you need it for a matter of definition. So just assigning the very concept of that, it's as if it starts infinitely fast and then slows to 0, or it's as if it begins and has a continuous gradation from 0 to 1 or 0 to infinity. A resistance is a quantity vis-a-vis just a constancy that it gets back, and then at some point in time there's just a plain linear constant input to arrive at sensibly a thing, because at some point in time, to be classical and sensible and linear, not only does it have to be 0, 1, but it has to arrive from 0 to 1, and it does so at a constant rate. Because this is Zeno's theory, and it includes all those things, and it's a classical theory. Not all people have all that theory, but pretty much everybody has a working theory where that makes sense. So he talks about propagation, the triangle theorem of Desargues, the principle of duality. That would probably be something relevant. Metric applications. So the last sections of each of these chapters look kind of like, well, this is kind of the outer view of these things. A projective generalization of a metric theorem. Non-homogeneous line coordinates. Analytic duality between point and a line. Cross ratios when the 4 elements are not distinct. So after something like, because the beginning of these sections are like simple rigid motions of the plane, cross ratio of 4 lines, point geometry and line geometry, division of a line segment. But that otherwise, this gets into a lot of quite interesting ways to to interpret the features, which while sensible among themselves, it's like, well, look at that. What do you know? It's like it's amazing. It's like I can't make any use of that. I know it's amazing, but I can't put a watch on it or put a measure on it. Can't get it back. It's kind of sensible, but it doesn't become fungible, doesn't become interchangeable, and there's other things. At the same time, it's like that's what's great about it. It's all that stuff has got to come together. All that stuff is part of it. So, along as this is part of a linear curriculum, it's saying is like we're not exploring all these trails right now. There's the principal branch is what we're on. But that's not the same thing as saying the other ones don't exist. But it does help to establish all the way along. It's like not only are we developing linearly, yet we're keeping it linear that anything else also so develops in its own way. And that no matter how it all works, that it all has to work together. Then for all these variations and the super classical notions, the very abstract notions, those do have their place as expressing the limits, the bounds, and even the very reasoning apparatus itself that always establish these complementary duals and the fuller dialectic. Not just didactic, but a fuller dialectic, as we're pedantic in our linear curriculum, which is the same for everybody, to be fair, and to be fair and also to be cumulative, and then that this higher mathematics is again lower mathematics, like that simple motion is a hyperbolic hypercube that is exactly 0, 1. Or is with regards to modeling any motion of any exchange of forces whatsoever in the classical, in the paleo-classical, and the super-classical, there's some of histories where it's at, some of potentials where it's going. Thus then that besides that advises our theory of least action with maturation and the fact that it is what it is, then there are also all the usual things that go into matters of action and the application of intelligence to information to gain mechanical advantage, to stand upright, or to turn a doorknob and open a door, then that's an extension of it, with as well that the origins are not so falsifiable scientifically, and the will or objectivity and subjectivity need not necessarily be so falsifiable scientifically, yet are perfectly yet suitable things in the theory for anybody. It's a strong mathematical Platonist's monist dualism with a strong scientism, although it's kind of that was once a bad word for people who use science wrong, and logical positivism, stronger logical positivism, which was words for people who's like, we don't really have logic anymore, like these classical laws, we're just making up axiomatics. We don't really have in the empirical anymore, that was this induction that was often wrong. We just have our new induction, we'll call it science. But there's stronger logical positivism with this teleological bit, the silver thread connecting it still. This is the way of things. So yeah, this book starts with 3 linear equations and 3 unknowns, parametric forms of objects in a 3-dimensional space. ax plus by plus cz equals d, or k here. The usual term for a constant, with a, b, and c being usual coefficients and x, y, and z being the usual names of the variables of the unit values in the Cartesian orthogonal vector basis, the Cartesian coordinate space of the space-like terms x, y, and z. A, b, and c geometries in the coefficients, x, y, and z, this analytical basis. Thus begins a book on geometry. Here the idea is that this axiomless natural deduction, which is constant, consistent, complete theory, deal with it. There is one. It's from nothing and it's from infinity. Axiomless natural deduction then arrives at, it's like, well, you got points on lines and they don't come together. How about a spiral space-filling curve and just a line drawing at all? So then the objects of geometry just kind of naturally just build out and fall back from that. And so you get Euclid's elements and Euclid's axioms also from nothing. Axiomless geometry. This is something that, for at least some strong mathematical Platonists of the mathematical philosophers, it exists. And it gives Euclid's elements. Well, good day, gentle readers, fellow earthlings. I shall so hope you enjoyed this today. It was to begin about hypercube distance, and that a path in this model, the hypercube distance, is a straight line. But then how it got there is just a way to effectively reflect that there are no straight lines. There are no right angles in a universe of straight lines and right angles, this continuous manifold in which we inhabit. So they go together. The inner and outer products, thusly, why the hypercube distance is 1. Warm regards.